Yes, dear students, I invite you to lecture 16 of micro irrigation engineering subject. This lecture is dealt with the numerical problems which has been the theory part of the subject on irrigation scheduling and then soil water concepts, which we have discussed in theory class. So, we will work out some numerical examples. So, this is tutorial class 3. Now, in this tutorial class 3, we will be working out problem on irrigation scheduling and irrigation efficiency and adequacy of irrigation. So, question 1 is on we have been given in this question there is a crop, wheat crop. A wheat crop requires 45 centimeter of irrigation water during 120 days irrigation period. So, crop duration is given as 120 days and the water requirement of crop is 45 centimeter. How much land area can be irrigated with a stream size of 20 liter per second when it is applied for 8 hours duration in a day. So, we are given depth of irrigation is 45 centimeter, we are given the base period, that is irrigation period is 120 days, and then water flow rate in the size of stream is 20 liter per second and irrigation time is 8 hours per day. So, total discharge during irrigation period can be worked out in a volumetric form. So, in 20 liter per second is the discharge. So, this is applied for 8 hours in a day time in one day, and then total 120 days is the irrigation period. So, 69,120 is the total volume of water which will be delivered by this stream. And then irrigation requirement, because we have been given the 45 centimeter. So, per hectare 45 centimeter hectare centimeter, rather we say 45 hectare centimeter, that can be put up in the volumetric form, that will be 45 into 10,000 square meter divided by 100, because this is in centimeter. So, it comes to 4500 cubic meter. So, area to be irrigated will be volume of water available, that is 69,120, because this is the discharge which is computed from this your 20 liter per second. So, this is the volume available water and volume of water required is 4500 cubic meter per hectare. So, this comes to 15.36 hectare. In question 2, the bean crop is grown in a clay loam soil and it is in mid stage. Mid stage means when we look at any crop, it is given by initial stage, development stage, then crop mid season stage and then late season stage. So, this particular crop is in the middle stage, and ground water table is 5 meter below the surface. So, it is assumed in this question the capillary water rise contribution from the water table is not will not take place from particularly in this cropped area. And at the beginning of mid season stage of the crop, moisture content is at field capacity. Okay, this is the another important information is given that moisture content is at field capacity. Reference crop evapotranspiration and precipitation values for 10 days period are given in the table. So, we have been given from day 1 to day 10 daily evapotranspiration of the crop, and then here the precipitation which has occurred, it has occurred on 5th day, day 5, that is a 5 millimeter of rainfall, and then on 7th day that is 0.2 millimeter it has occurred, and rest of the days there is no rainfall. So, we are given reference evapotranspiration and the precipitation. Here it is assumed that effective root zone depth of the crop is 60 centimeter. Crop coefficient at the middle growth stage, mid growth stage, it is 1.05. Volumetric water content at field capacity and wilting points are 36% and 18%. So, field capacity moisture content is 36% and the wilting point moisture content is 18%. Crop stress coefficient Ks is 1 and depercolation loss is considered negligible. We need to use these data to schedule irrigation on a fixed interval of a week, that is at a weekly level we will the irrigation is given, and if management allowable deficit, that is a MAD it is written, this is a management allowable deficit is assumed as 50%. So, once again I am reading the data which are given in the question. Moisture content at field capacity is 36%, permanent wilting point is 18%. So, available water content is 36% minus 18%, that is the available, that is 18% is the available water content. Effective root zone depth is 60 centimeter, crop coefficient at the mid growth stage is 1.05 and maximum allowable or management allowable depletion is given as 0.5. So, total available water, as I told you, 18%, which I can write 0.18 multiplied by 60 centimeter is the depth, effective root zone depth. So, this is 108 millimeter total, this is total available water, and management allowable depletion is will be given, means amount in terms of allowable deficit, means that is your the in terms of depth one can find out. So, 50% of 10.8 centimeter, it is 5.4. So, it is a 54 millimeter will be the allowable depletion. So, the moisture content at the beginning is field capacity, means we do not have to give irrigation. So, moisture content in the previous day, soil moisture depletion in the previous day, that is I minus 1 is equal to 0. So, soil moisture depletion at ith day can be given by soil moisture depletion in the previous day plus E T naught on a particular day plus KCI crop coefficient of ith day, KSI that is the crop stress coefficient on ith day, Ks plus depercolation loss on ith day. So, this is given as 0 and precipitation values for the 10 days period, these are available. So, on 5th day and 7th day rainfall values are available to us. Now, this water budgeting has been made for from day 1 to day 10. So, the moisture content, soil moisture depletion in the previous day was 0, ET naught 5.6 millimeter, KCI 1.05, that is in the mid stage, it is given in the question and that is taken as a constant for all the days 10 days, and same thing crop stress coefficient for all the 10 days. So, these are given as 1. Now, we will calculate the ETC, that is evapotranspiration requirement of the crop on ith day, that is day 1, it is nothing but 5.6 multiplied by 1.05. So, we will get 5.9 millimeter. Depercolation, it is negligible. So, it has been taken as 0. Precipitation on this day is 0. So, this value is 5.9 millimeter is the soil moisture depletion at on day 1. So, this becomes your for next day, that this becomes your for second day is the initial soil moisture content for day 2, and then ET naught is given. If you see from the table, it is 5.4, this is multiplied by 1.05 and this is 1. So, this becomes 5.7. So, 5.7 plus 5.4, it becomes 11.5 sorry 5.9 plus 5.7, it becomes 11.6. So, like this we will be calculating these values. So, this 11.6 plus 6.2 which has come from these two values. So, 11.6 plus 6.2 is 17.8. Now, 17.8 becomes the moisture content in the previous day, that becomes your the initial value for this to start with. So, this value plus this value will give the new value like this, and then it will be subtracted in the next when you are doing it. So, you are doing it this calculation and then you what you are doing, you are subtracting, and this like this these values are estimated for all the 10 days. So, for management or maximum allowable deficit based scheduling, 54.2 millimeter will be the irrigation depth that would be required in the morning of 11th day. On the means on the morning of 11th day, 54.2 millimeter it will be the depth of irrigation, whereas when we are giving irrigation based on weekly period. So, on weekly period, that is on 7th day when you are doing it, this is the depth of water which will be needed on 11th day after a week. So, this way one can work out these values. Question 3 is we are required to calculate irrigation interval for a crop which has effective root zone depth of 146 centimeter, grown in a soil which has field capacity of 14% and the permissible soil moisture depletion of 7%. The monthly evapotranspiration of the crop is 285 millimeter. There is an effective rainfall of 35 millimeter during crop season. So, let us try to learn from these data. We are means we have been given moisture content at field capacity is 14%, soil moisture depletion is 7%, effective root zone depth DRZ is 140 centimeter, effective precipitation is 35 millimeter and crop evapotranspiration is 285 millimeter in a month, and we are required to calculate the irrigation interval. From these given data, we are interested to know what is the what will be the irrigation interval, means what will be the next irrigation we should give. So, irrigation interval is determined by using this particular expression, which is given by moisture content at field capacity minus moisture content, that is a depletion, or we can say permissible depletion, that is a critical moisture content, or we can say. So, this is 7% given, field capacity is 14% it is given, depth of root zone is given as 140 centimeter, plus the effective rainfall is 35 millimeter, Pe divided by ETC, that is daily, means when we are talking about ETC, here it is a daily, that how much is the evapotranspiration, daily evapotranspiration requirement. So, simply what we are doing, 14.14 minus 0.07 multiplied by 1400 millimeter plus 35 millimeter is the rainfall, divided by 285, because it is a per month. So, we are taking 30 days per month. So, we get irrigation interval of 14 days. So, next irrigation will be provided as after 14 days interval. Question 4, here it is given an irrigation stream of 1800 liter per minute is supplied to a farm daily for 24 hours. Here irrigation stream discharge is known to us, and daily this particular irrigation stream is operated for 24 hours, means every day for 24 hours this stream is supplied. And maize and wheat are the crop which has area of 0.8 hectare, and then wheat has area of 1 hectare, and they are daily irrigated. Irrigation requirement of maize is 8 centimeter, mean daily 8 centimeter of water is needed, and 12 centimeter of water is given to wheat crop. Compute the irrigation efficiency of the system, irrigation system. So, here we have been given water means diverted from the field is 1800 liter per minute, and then irrigation interval is 24 hours per day. Area of maize is known to us, area of wheat crop is known to us, and then irrigation requirement for both the crops are given as 8 centimeter and 12 centimeter for wheat crop. So, irrigation requirement for the wheat crop is given by irrigation. First we will calculate the amount of water supplied to the farm is we are given 1800 liter per minute. So, 1800 into 60 multiplied by 24 divided by 1000. So, 1800 liter per minute. So, this is given as a in 1 hour, we will multiply it with 60, and then daily irrigation is given. So, this will become 24 hours. So, here and divided by 1000 means to convert into the cubic meter. So, liter is converted to cubic meter, and then the per minute is converted to daily 24 hours. So, this total volume of water supplied to the farm is 2592 when we calculate. Then when we are calculating volume of water required to irrigate maize crop, it is given as 8 centimeter. So, 8 divided by 100, so it becomes in meter, and then area is 0.8 hectare, area of maize crop is 8.8 hectare. So, 0.8 multiplied by 10,000 square meter. So, this will become 640 cubic meter. So, volume of water required to irrigate wheat crop, similarly we will calculate. So, 12 divided by 100, it will become 0.12 cube meter multiplied by 1 hectare. So, 1 into 10,000 square meter. So, 12 by 100 multiplied by 10,000 will give us the volume of water required to irrigate wheat crop. So, total volume of water required can be calculated, that is total volume of water used for irrigating maize and wheat crop is 1840 cubic meter, and then we have the water supply to the crop. This we calculated from the stream of 1800 liter per minute. So, this is 2592. So, and then 1840 divided by 2592, it gives the value of 70.99% or 71% is the irrigation efficiency. So, here 71% of the water applied is beneficially utilized by the crop, while 29% of the water can go as a loss in the form of depercolation or in the form of runoff or evaporation or spillage, that could be. So, this is a quite a good good way of the supply of water by using this stream. Question 5 is also on the efficiency side. So, stream of 135 liter per second was diverted from a canal, and this water reaches to the field is where it is measured only 100 liter per second, from which only 100 liter per second it has been delivered to the field. So, there is a considerable loss in the water through conveyance system. An area of 1.6 hectare was irrigated in 8 hours by using the stream of 100 liter per second. The effective depth of root zone of the crop is 1.8 meter. Runoff loss in the field was 432 cubic meter. So, at the at the downstream end of the field, runoff was measured, and it is found that 432 cubic meter water goes as a runoff loss. The depth of penetration, when we measured that how much amount of water it has infiltrated below the ground level. So, it is found that 1.8 meter at the upstream end, that is head end, and 1.2 meter at the tail end. This is the normal thing, it happens in the field when irrigation is given. So, at the upstream end there is a more loss of water through infiltration process, and when it comes to the downstream end. So, there is a less opportunity time for the infiltration to take place. So, the at the downstream end it is only 1.2 meter. So, available moisture holding capacity of the soil is 20 centimeter per meter depth of soil. This is nothing but the water holding capacity or field capacity of the soil. Now, we are required to determine the water conveyance efficiency, we are required to determine the water application efficiency, we are required to determine water distribution efficiency. 3 efficiency terms have been have to be evaluated by using the data given in this question. So, once again I am reading here, water delivered from the source is 135 liter per second. Water delivered to the field is 100 liter per second. So, this water which is delivered to the field is for 8 hours. Area of irrigation is 1.6 hectare. Runoff loss is 432 cubic meter. Effective root zone depth is 1.8 meter, and this is already I have told you that moisture content at the field capacity is 20 centimeter per meter. So, conveyance efficiency is computed by volume of water, means it is water delivered to the field to the, it is the ratio, this is the volume delivered to the field to the water diverted from the source. So, water delivered to the field into 100. So, water delivered to the field is 100 divided by 135 into 100, it gives 74% is the conveyance efficiency. Water stored in the root zone is water delivered to the plant minus runoff loss. So, in this question we know that how much is amount of water delivered to the field. We have the stream size of 100 liter per second. So, this 100 liter divided by 1000 will give cubic meter, and then this water is supplied 8 hours. So, we are converting this is in cubic meter. So, volumetric form. So, this will be multiplied by 60 into 60 into 8. So, means we here the liter per second is converted to per minute, then per hour, then 8 hours it has been supplied. So, this will become the water delivered in the volumetric form minus 432, it has gone as a surface runoff loss. It is assumed in this question that there is no deep percolation loss. So, once it means, so this once we are assuming that there is no deep percolation loss. So, 2880 minus 432, this is the effective amount of water stored in the root zone depth. So, this way having got the value of water, volume of water stored in the root zone divided by volume of water diverted to the field will multiplied by 100 will give us the water application efficiency. If we could have been given amount of water which had lost below the root zone depth, then in the amount which we have got 2448, we will subtract the volume of water which has gone beyond the root zone depth as a deep percolation loss. Then in that case your this volume will be reduced to that particular value. So, this way we are calculating the application efficiency. Now, water distribution efficiency is given by the 1 minus y bar divided by d bar into 100. So, what is y bar? Y bar is the this numerical deviation from the mean value of depth of infiltration. So, this is at upper end we are seeing that it is 1.8 meter minus 1.5 meter. So, this 0.3 meter is the amount of water it has gone as a numerical deviation. So, at lower end, so how much is the loss we are getting 0.3 meter. Average values, how we are getting average values, we are taking only two values, what is given in the upper stream means head end, and what is the amount of water which has gone as a infiltration at the downstream end. So, this is average of 1.5 meter. So, this value will give us the numerical value, and then accordingly we will calculate. So, this numerical deviation y bar is 1.8 minus 1.5 is 0.3, and then average value is d bar is 1.5. So, water distribution efficiency is 80%. So, this way we calculated in the problem, we calculated the conveyance efficiency, we calculated water application efficiency, we calculated water distribution efficiency. In question 6, we are given depth of infiltration measured around the field, and this field is quite large, where at every unit, that when we are dividing the whole field, let us say in 20 grids, and each grid is of the some certain percentage of the total area. So, the values of each unit, that is say when we have got the 100% area, and if we are dividing, this is the matrix which we are seeing here. So, there are 20 grids. So, 5 by 4 matrix it is formed, and for each area how much it is represented by infiltration rate. So, it is given 4 centimeter depth of infiltration, cumulative depth of infiltration is 4 centimeter in first 5% area, then 3.5, then 3.4, 3.7, like this for all areas 5% each, the values of infiltration has been obtained, and we are required to obtain the adequacy of irrigation for the field if full irrigation is given as 3.25 centimeter. So, desired full irrigation is 3.25 centimeter. We are required to, so those data which we have, these data which we have, these data we will be putting in the descending order of the magnitude, and then we will compute the percent of the field represented by each depth. So, then we will compute the cumulative area of each depth, and we will find out the cumulative area versus depth, and then from this cumulative area frequency curve we will get the adequacy depth adequacy of irrigation from the graph. So, what we have a data, we have got the infiltration data of 4.3% like this. As I was telling you, there are 20 number of depth of infiltration which has been obtained, and each depth is representing the 5% of the total area. So, 5% you can see here, and then what we are finding out? We are finding out the cumulative area. So, 5 plus 5 10, then 10 plus 5 15, like this. When you see the 2.6, that means 2.6 we are getting the total area, it is 100% cumulative area. So, from these data we will get cumulative frequency curve plotted. So, cumulative frequency it is the depth of water infiltrated versus percentage of the field area. So, this curve which is plotted, this curve is nothing but frequency of cumulative frequency curve. And so, this cumulative frequency curve, we are given the full depth of irrigation which is required. So, when you are plotting say 3.25 is the required depth of irrigation, and which touches this or which crosses the curve, it is at 67% of the field area. So, adequacy of irrigation is 67%. Now, these data of adequacy of irrigation is used to evaluate or interpret the data for effectiveness of irrigation when how the uniform water, application efficiency and adequacy, these three terms are utilized for finding out the effectiveness of irrigation. So, you can refer these books for as well as the internet material for more examples to work out more problems related to these topics. So, here let me summarize. We worked out the problems related to irrigation scheduling, we worked out problems related to irrigation efficiency, we worked out problem related to adequacy of irrigation. Now, in the forthcoming lecture, we will learn about water lifts and pumps. Thank you very much and good day.